This is something that, for you all that had Chem 1 last year, we were supposed to get to fourth 9 weeks, but lo and behold, we weren't able to because we had to do all that fun blended learning and stuff. Okay? Now, there's quite a few gas laws and everything, and you're going to kind of see some very same letters throughout this whole process with these different gas laws and everything. You will see a P. What do you think P is going to stand for?
Pressure.
Pressure, right. Okay, now with pressure, we can have a couple different units with it, possibly. One of the units that we can possibly see is called atmospheres, or atmosphere. And it's abbreviated ATM. We're going to have a kilopascal. KPA. Okay, we can have millimeters of mercury. mmHg. Another unit is torrents. Abbreviated as TOR. And I think that's all the ones that I would kind of worry about for right now, okay? Now there's other units that we can possibly use and everything, but these top three, or I guess you can kind of consider them as the main ones and everything. Now if you need to convert from one to the other, there are the conversion factors that we need to use for those. And we'll kind of work our way down. So if we start with 1 atmosphere, or atmosphere, it's the easiest number because it's always going to be 1 in this situation. Okay? So 1 atmosphere would equal to 101.325 kilopascals, which is also equal to 760 millimeters of mercury, which is also equal to 760 torr. All 4 of these numbers are equal to one another. And if we look at torr in millimeters of mercury, what can we say about those 2 units?
Appear to be the same.
They're on a 1-to-1 ratio, right? Because both of them have 760 to it, right? All right, now another unit or variable that we're going to see a lot, V. What do you think V is going to stand for? Volume. And we're also going to see T.
Temperature.
Temperature. Now, one of the things you got to remember with gas laws, temperature, it needs to be in Kelvin. So, you all remember how to convert from Celsius to Kelvin? Yes, no, do we need a little refresher?
Refresher.
Refresher, okay, Kelvin is equal to our temperature in Celsius plus 273.15.
I was like 271.
You're close.
I was thinking like 132. You're closer to me. Okay, Adam. Did you you eat breakfast?
Actually, I did, yeah.
Did
I-
you
I
really?
Did you
spent
actually?
2 whole days and a lot of caffeine reading it.
Did you actually?
Yeah, I read it all.
I haven't even read all 6 yet.
I read all
Me
3
neither. I'm not going to either.
I think on the syllabus it said you have to
It was literally probably like
We're going to
This is
eventually
probably
that.
like 8 to 10 hours and
All right.
600.
I think I have a typewriter for that too. I have a-
First 3 gas laws that we're going to talk about, they all have one thing kind of common with one of the other ones. All right. First one's called Boyle's Law. I'm going to give the very condensed definition for these things. Okay? Okay, so volume varies inversely to pressure if temp is constant. So what does that mean? One goes up, the other one's going to
go down.
go down, all right? If temperature is constant. Now, is this important to us? Oh, yeah, absolutely. This is very important if you're, particularly if you're like a deep sea diver. Okay, so let's kind of think about it. Why would this be important for a deep sea diver? Okay,
Well, because the pressure goes up immensely as you go down farther.
that's the liquid, we're talking about gases. Okay, so as a diver is going to ascend, which means go up, they tell that diver to sing a song. Okay, instead of holding your breath. Because yeah, down at the bottom of the ocean, a lot of pressure. I agree with that. Okay, now, if you hold your breath while you're ascending, what's happening to that pressure? It is decreasing. So that means that the gases inside your body are able to expand more. So if you hold your breath while you are ascending and not singing your song,
Your lungs might get popped.
your lungs are going to swell up like a balloon to the point that they will rupture. Now, another thing, while they ascend, they cannot go higher than their air bubbles. What happens if they go higher than, if they go faster up to the surface?
Their brain pops.
No. They get what's called the bends. Nitrogen gas inside their blood becomes undissolved and turns into a gas. And so you get nitrogen bubbles in your system, and it causes them severe pain that they bend over. Yes. So they have to go into a decompression chamber and stay there for a couple days while the nitrogen gas gets slowly dissolved back into their blood.
I think I'll stick the notes.
All right, so gas for the formula for Boyle's law, P1 times V1 is equal to P2 times V2. Okay, now I know this is a stupid question. Does anybody have any dry erase markers?
I do.
Okay, I need.
I have one too.
Why?
Why don't you?
I don't know how well that's gonna
Why
work
would I
out.
have dry
I think I
erase
have
markers?
one. Mine are prettier.
Mine's black.
Yeah.
Like your soul. Variety.
Thank you, thank you, thank you. All right, so P1 times V1 is equal to P2 times V2. Real simple formula, okay? Now, for a lot of these problems and a lot of these gas laws, we're going to have we're going to have at least 4 variables in it. You'll be given 3 variables. Find that unknown. And what we'll try to do is we'll, if we have some time, we'll look at some examples and everything, probably like from that assignment that I'll post for you all. All right? All right, next one. Next one is Charles' Law. Charles' Law states that volume is directly proportional to temperature if pressure is constant. All right, so something is directly proportional. If one goes up, the other one
Goes up.
as well. So formula for Charles' Law, V1 over T1 is equal to V2 over T2. Next one is Gay-Lussac's Law. Gay-Lussac's Law is very similar to Charles' Law, but we're going to switch 2 words around. We're going to switch pressure and volume. So pressure is directly proportional to temperature if volume is constant. Alright, so since we're only switching pressure and volume in our definition with the formula, instead of having V1 and V2 up in the numerator, we're going to have V1 and P2. Okay, P1 over T1 is equal to P2 over T2. Now, as I said, all 3 of these first three gas laws, you see how they have something in common kind of with one another? So like got Boyle's and Charles, what do they have in common with one another? Volume. Okay, Boyle's and Gay-Lussac's. Pressure, Charles and Gay-Lussac's. Temperature. Okay, so sometimes we can't keep one of these variables constant. Everything changes. Okay? So if we have a situation where everything changes, we have what is called the chaos combined gas law. Now, with the combined gas law, we're going to combine all 3 of these into one formula. So if we look, well, all right, Boyle's law has P1 times V1 is equal to P2 times V2. Gay-Lussac's has pressure up in the numerator. Charles has volume up in the numerator, correct? Okay. P1, V1 is equal to P2, V2. Now, both Charles and Gay-Lussac's have temperature down the denominator.
You just put all over there.
Any questions so far? No questions? All right. Okay, next gas law is probably the toughest gas law that we have. Okay, Next one is called Dalton's Law, or Dalton's Gas Law, whichever one you want to call it. It states the total pressure of a system is equal to the sum of the partial pressures of the gases.
We are ready for peer tutors. Please head down to the gym.
What's happening?
I didn't bring anything.
If you need to go, you need to go. All right, so how do we write out the formula for Dalton's Law? Well, we kind of follow it. It says total pressure of the system. Excuse me. P tot is equal to the sums of the partial pressure of the gases. Equal to P1 plus P2 plus P3, so on and so forth. What?
The heater tot sounds really good.
What?
I brought the Diet Coke and Mentos and the Pepsi and Peeps.
Okay.
In case you want to explore that.
Wait, what?
What?
We'll try to do some demos maybe on Wednesday or something like that, since that's
I
going to be
guess
our last
we
day in here.
usually do.
That's fine.
We're going to try to do some fun stuff. Okay.
Yeah.
Craig, we gotta go out with a bang on the last day, okay?
All right. So,
We gotta go out with a bang.
Dalton's Law.
I don't know what I'm talking about when I'm saying bang. We blow out the school.
Yeah.
She said it, she said it.
What do you do, fire you?
all right, now, next one. If we are behaving under ideal conditions, we can have what's called the ideal gas law.
California.
Ideal gas law.
What you just said?
PV is equal to nRT. 3 out of the 5 variables, you already know. P stands for pressure. V stands for volume. T stands for temperature. Okay, so the two that we haven't talked about today. N number of moles. So for these types of problems, if you are given a certain amount of a gas, mass of a gas,
Yes, man.
more than likely you're going to have to use the ideal gas law in this situation because this is the only one that has the number of moles with it. Okay? Now, R,
High school FFA, please head to the gym.
I miss up there.
I know.
if they call your group down, go ahead and go on down. Come back as soon as you can. R stands for the ideal gas constant.
What are?
Shut up.
That's what they chose.
It's just taking one slow breath at a time.
Oh.
Because G is used for other things. Okay, so the ideal gas constant, we can actually use two different numbers for this one, depending upon what unit of pressure we have. Okay, so one of the R values that we can use is 0.08206. Some of you have kind of seen this before.
No.
We usually do that in the worksheet, like, that's an idea.
I think we use this for the R value when we're dealing with equilibrium going from KFC to KFP.
That one.
Yeah. So 0.08206. Now, this constant has 4 different units with it. Liters times atmospheres over moles times Kelvin. The other one that we can use,
Peer tutoring is heading back, and we are ready for Sunshine Society.
8.314 liters times kilopascals all over moles times Kelvin.
Did we even have Sunshine Society this year?
That's what
I didn't think so.
Look at, they didn't do a dance.
They didn't do anything.
Meetings or call-outs for it.
La-di-da.
You weren't invited. I wasn't invited. Probably not.
Any questions there? No? All right. Now for the gas law, let's talk about two different terms that we can use. Diffusion and effusion. Okay, diffusion we are going from an area of higher concentration to an area of lower concentration. Okay, so kind of bring up this, some of you said that your parents are into the essential oils and all that stuff. Did they have a diffuser?
Yes.
Okay,
Mom
so
has like 3.
okay, so diffuser is that. So the area of higher concentration is that little plate that has the oil on it. The area of lower concentration is the house. Okay? Or another example. Probably all have had this happen here at school, or when you go off to college, you'll definitely have it happen there.
Did you say death?
That one person that likes to put on cologne or perfume instead of taking a shower. There's usually that one person, freshman year on your floor, okay? And
I feel like there's multiple people.
they bathe themselves in that stuff. So, area of higher concentration, when you were able to use your lockers, probably would be at that locker, right? Area of lower concentration, rest of the hallway.
FFA is heading back. We are ready for guidance helpers.
That's a clump.
Okay, now, effusion. How fast a gas can escape through a tiny hole. And how we came up with fusion, there was a Scottish scientist, last name Graham, and he came up with Graham's law.
Rambo.
Not have a law.
Now, Graham's law does deal with diffusion.
Dude, that is so nice house. It's really the depth, man.
Okay. So the rate of diffusion is equal to the square root of the inverse of the molar masses. And when we are calculating out the rate of fusion, we're always comparing two different gases to one another.
Sunshine Society is heading back. We are ready for office helpers.
Guidance helpers is the last one. Idiot.
Okay, so rate of fusion, so rate of gas A over the rate of gas B is equal to square root molar mass of gas B
Also teacher aides.
over the molar mass of gas A. All right, so now rate of diffusion. Let's kind of think about this. Let's look at balloons. So, if you got a bag of balloons at home, take one out, put your mouth on it, you expel a gas into it, right? What is that gas that you're expelling into the balloon? Carbon dioxide. Now, if you go to like beer, caramel, something like that, you get a balloon, and the balloon's floating up in the air. That balloon is filled with helium. Okay, so helium is a lot smaller than carbon dioxide. Would you agree to that?
Yeah.
All right. So what we can do is figure out, because compare a helium balloon to a balloon filled up with carbon dioxide. What's going to happen to that balloon filled up with helium over a period of days?
Same.
It's going to start falling to the floor, and what's going to happen to the size of that balloon?
It's gonna decrease.
It's going to decrease. Now, compared to a balloon that's filled up with carbon dioxide, that balloon that's filled up with carbon dioxide usually kind of stays its shape for a very, 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 very long time, right? Now, would you also agree that latex balloons they usually get with this stuff in, very porous? Latex means it has a lot of holes in it, right? Okay, so what we can do is we can figure out what is the rate of diffusion of helium compared to carbon dioxide, and see why that helium balloon is going to shrink and fall down to the floor a whole lot faster than that carbon dioxide balloon shrink. Okay? All right, so the rate of fusion, rate of helium, because that's going to be our gas A, because that's what the one that we're looking for, is equal to the rate of carbon dioxide, square root. Now, we have to flip the molar masses. So carbon dioxide, what is its molar mass? Well, carbon has a mass of 12.01, 2 oxygens, that's 32. So 12.01 plus 32 is 44.01 grams carbon dioxide. Now, if we look at the periodic table, helium has a mass of 4.00, right?
Just a little bit less.
So you're looking at all the small numbers on the side, and then it's the big one in red. I'm like,
All right, so what is our number? Well, let's kind of run this through the calculator. So I'm going to take square root of 44.01 divided by 4. Now, if we look at our masses, carbon dioxide is roughly 11 times bigger. Agree? Okay, so I'm coming up with a number of 3.32, and the rate of fusion is just a number. There's no units with it. Okay? So this is telling us that helium fuses 3.32 times faster than carbon dioxide. Okay? Questions? Any other questions there?
How was your weekend?
Let's get done with this first.
Okay.
wrong question.
Any questions over gas laws?
Are there more gas laws?
There are a couple more, but with the Ivy Tech, we're not going to worry about them.
We're ready for SCCLA.
Then one of them kind of goes along with
Which one is it?
what is the actual volume, and we can bring in some variables because of intermolecular forces and everything like that. But I'm not going to be overly concerned with that right now, because with a lot of Chem 1, this is what we get with freshman chemistry in college. This is what we're going to talk about. Okay. So any questions there? Nope. All right. We can go ahead and stop recording.